So before we add additional statistical techniques to our toolkit, I think it's important for us to step back away from the mathematics or statistics and think again about what we're actually asking statistics to do for us. And almost in all cases of inferential statistics, we're asking these mathematical equations to test hypotheses for us. So I think it's important for us to take a step back and talk about what do we mean when we talk about hypotheses, and how do we actually word hypotheses to make them easily tested. So hypotheses are predictions about specific events, and these predictions that are often about the causal relationship between two more variables. So it doesn't have to be causal. And remember that causation has a set of methodological requirements for us to be able to talk about causation, which includes temporal precedence, that we have to know our IV happened before our DV, and generally the only way to know that with certainty is if we control it. However, generally across the board, any hypothesis is a statement of a prediction. A variable or variables is related, potentially causally, to other variables or variable. So when we talk about a causal hypothesis, it is a statement of relationship between an independent and dependent variable at its most basic form. And again, there could be multiple independent variables and multiple dependent variables, but generally, when we're talking about hypotheses, we want to make sure that they are individually testable. So a lot of the times, if we have a more complex hypothesis, we may actually have a series of hypotheses talking about each relationship that we're interested in looking at. So a causal hypothesis describes a cause and effect, and it's usually stated in two forms. Actually, I should be a little bit more careful here. It's stated in one form, which implies a second form. So the null hypothesis is usually not actually stated. It is assumed. And the null hypothesis basically is that there is no relationship. The alternative hypothesis is usually the one that we will write out. So for example, a null hypothesis about anxiety and depression is there is no relationship between anxiety and depression. An alternative hypothesis, which is the one we would most likely state and test, would be that we expect there to be a positive relationship that as anxiety increases, so does depression, or vice versa. So the two forms are mutually exclusive and exhaustive. So when we're creating an alternative hypothesis, one of the ways, remember I talked about testability and falsification, that a good scientific hypothesis needs to be testable. In other words, multiple people could test it in multiple ways, and it needs to be falsifiable. In other words, data should either support it or refute it, which means that when you create the alternative hypothesis, you should ask yourself, what is the null hypothesis, and could it also be confirmed? If so, is it mutually exclusive and exhaustive? In other words, the only options from this are the study should be able to either support the alternative hypothesis, the stated hypothesis, or support the null hypothesis, that there is no relationship. Good science usually has this. The two forms are mutually exclusive and exhaustive. So let's just go through some examples of what hypotheses look like. So for example, it is expected that an IV will cause an increase in a DV, or it is hypothesized that an IV will be related to a DV. That's an example of two different types of hypotheses. The first one is more causal. The second one is more of just a pattern or a relationship. So again, the first one, if done correctly, would be a true experiment. The second one, if done correctly, would most likely be more of a quasi-experimental design. Remember, the quasi-experimental design either means that we did not take temporal precedence, in other words, we're not in control of the IV, it's a pre-existing IV, or that we don't necessarily have a causation and we're looking more for relationships. Both of these are quasi-experimental designs. So specifically, it is expected that children in academic after-school programs will have higher IQ scores than children in the general population. Or it is hypothesized the amount of food eaten will increase as portion size is increased. Notice both of these are fairly directional hypotheses. Both of them expect a specific direction of the relationship. So as children in after-school programs, so that's you either in it or you're not, but if you are, it's expected you'll see an improvement, a positive effect on higher IQ scores. Also the second one, as the amount of food is increased, so will the portion size, or vice versa. Now notice that we would have to actually methodologically take control if we wanted to truly say there was a causation. So for example, both of these could lend themselves to either a quasi-experimental design or a true experiment. So the top one in a quasi-experimental design would be that we take pre-existing kids, so kids that have chosen to be in an after-school program versus kids that have not chosen. We then measure their IQ. If we find a difference, we can say the evidence seems to indicate that kids that choose an academic after-school program tend to have an higher IQ. But is that being caused by the after-school program? Or is it that children that choose after-school programs aren't naturally more intelligent? It could be that IQ is what's driving that choice. So we don't know which one is first or second. However, we could also set up a true experiment where we take 30 children and randomly assign them to either be in an academic after-school program or not be, and then look at their IQ both before and after. If we found that their IQ of the two groups was the same beforehand, we then randomly assigned half of them to go into an after-school program for one semester. And at the end, we gave an IQ score and found that the children in the after-school program on average scored higher than the children that did not go to the after-school program. Guess what? We've got a pretty good argument for causation, that after-school programs do increase IQ. Notice that a lot of times when you read studies, they don't actually go through this process of doing a true experiment. A lot of our assumptions are based on quasi-experimental studies, and those quasi-experimental studies, you always have to ask the idea of correlation does not always equal causation. Just because there's a relationship doesn't mean that one causes the other. And likewise, we could simply look at kids that get larger portion sizes. Do they eat more? But again, are they eating more and that's why they get larger portion sizes, or are the larger portion sizes resulting in eating more? We could also take control of this and make it a true experiment where we take a group of kids and again, take their breakfast, lunches, and dinners that are being provided by the school and then assign them to either a larger portion or a smaller portion size with the ability to get extra food if they wanted, and then see if the actual amount of food is changed. In other words, do the kids that get less portion basically eat what they're given and then don't get more? And the people that are given more food eat more and basically finish their plate? Or are the kids that are getting less just going getting extras afterwards? Again, we could look at that both ways. So if we look at these again, the top one, the IV is participation in the after-school program, the DV is IQ scores, and the bottom one, the IV is portion size, while the DV is the amount of food eaten. So again, hypotheses can be null, predicting no relationship between variables or no effect on one variable and the other. In other words, our null hypothesis, often represented by hypothesis 0, or HO, equals the first mean will equal the second mean. There is no real difference. The alternative hypothesis is predicting a relationship or an effect. And generally, if possible, if past theory allows it, we want that to be directional because it's more likely we'll find an effect if it's there. So a directional hypothesis predicts the direction of a relationship. In other words, we often refer to this as HA, or hypothesis alternative. So the first mean is greater than the second mean, or the first mean is less than the second mean. Both of those are directional hypotheses. So a causal hypothesis one tail, we have the hypothesis, employee training will reduce employee absenteeism. We have the null hypothesis, there will be no change or will be more absenteeism. In other words, again, the null hypothesis needs to be exhaustive. Any other possibility other than the hypothesis. It's one of the reasons that it's a little bit more likely to find the effect if it's there because there's more in the null hypothesis. Again, think of this as a two-tailed test, that employee training affects employee absenteeism. That means both positive and negative are in the hypothesis, and now the null is only no change, which means it's a little harder to find that relationship on the top because it's a two-tailed test. The alternative hypothesis might also be there will be less absenteeism as a result of training. So again, we have the hypothesis, we have the null and alternative, the two ways that we can word it. And again, when we look at this, we can think about this as far as the one-tailed test. If we're looking at there will be less absenteeism and we're measuring absenteeism on a 0 to positive scale, we're only looking to see, does the actual training get people to do less absenteeism? We don't care if they do more or equal, no change or more. So again, that's the advantage of the one-tailed test. So again, let's talk about the two-tailed test. So alternative hypotheses just predict a relationship or an effect. Hypotheses predict a relationship or effect, but not the direction or relationship with effect. It's a two-tailed test. For example, in this case, HA, hypothesis alternative, is that the mean from first group will simply not equal the mean of the second group. We're usually going to use these when we're doing more exploratory research, and there's not a lot of research that tells us a direction that we'd expect to find. So again, the two-tailed test, the hypotheses, our new drug treatment will cause a difference in depression. The null, there will be no change in depression as a result of the treatment. And the alternative, there will be a change. It might be positive, it might be negative in depression as a result of the treatment. And again, in this case, when we look at this two-tailed test, we now have the null hypothesis only being no change, with both less and more being a possibility of change, which is one of the reasons that it reduces the overall strength of the test, because we need a higher critical value for us to claim statistical significance, because we're looking at both tails. So again, let's just walk through some examples and look for the IVs and DVs. It is hypothesized that amount of food eaten will not be related to portion size. So this is a null hypothesis, not related. And we have, it is hypothesized that amount of food will increase or decrease. This is a non-directional or two-tailed hypothesis. And finally, it is hypothesized the amount of food will increase as portion sizes increase. This is a directional or one-tailed alternative hypothesis. So again, not related, will increase or decrease, will increase. So let's go through some more examples. It's expected that children in an academic after-school program will have higher IQs than children in the general population. So again, we have a directional alternative hypothesis. We'll have higher IQ scores. It is expected that IQ scores of children in academic after-school programs will be equal to those children in the general population. So this is a null hypothesis. We're expecting there not to be a difference. And finally, it's expected that IQ scores of children in academic after-school programs will be different from those in children in general. This would be a non-directional or two-tailed alternative hypothesis. It's just a difference. So hypotheses do influence the selection of manipulations. So how you actually manipulate or measure your IV, how you manipulate or measure your DV. It includes the selection of how you're going to actually measure outcomes, your DV, and also the selection of the research design. So if all we're looking for is a difference, we may be using a different statistical technique or a different bar for when we accept a p-value or statistical significance compared when we're not. So it is important to know what our hypotheses are. Are they alternative? Are they null? Are they exhaustive? And are they one-tailed or two-tailed, directional or non-directional? So the main points here is predicting no relationship or effect is indeed a hypothesis, but it's often not the focus of research. It's often unspoken, and it's more of a part of making sure that we have an exhaustive and complete way of looking at the test and to make sure that it's falsifiable, that we can actually find results that would indicate that we're wrong. Hypotheses that predict a relationship or effect need not specify the direction of the relationship, but they often do. And this isn't just chosen out of, I want a more powerful test, so I'm going to just randomly decide on a direction. It's usually going to be based on past research and past theory. And it is very important to use the research design and statistical procedure that's appropriate to the hypothesis you choose.